here. That's good enough. All right. Good morning, lads and ladies. Welcome back to Calc 2. Let me close my door here and we can get moving. Today, we're going to continue exploring the calculus operations that we can do with parametric curves. So last time, and last two meetings, I suppose, really, we've been talking about things like finding tangent lines, mins, maxes, and even areas bounded by parametric curves. Today, we're going to introduce two new operations. We're going to focus primarily on the first one. And these are of especially large importance in the fields of physics and differential geometry, which is sort of the mathematics, among other things, the mathematics that underlies general relativity, but also very fascinating stuff in its own right. I'm talking about arc length. Arc length and its kind of higher dimensional brother, surface area. Let me go ahead and turn on the screen share here. We can get rocking and rolling. Arc length is one of those lovely onomatopoeic things that is precisely what it sounds like, but it is not the simplest thing in the world to calculate. Before we get into that, this is MAC 2312, section number 004. The date today is the 11th of April, 2022. I think today is a good day to sort of remind you of a few things. So let's start with a couple announcements. We are, of course, nearing the end of the term. There are 2 weeks left. So big things coming up that we need to prepare ourselves for include exam 3 and the final exam. So I just want to start dropping occasional reminders specifically about the final. Pop up your syllabus. All right. So your final exam is on the 27th at 10:30, and the 27th, I believe, is a Wednesday. Yeah. So I want you to put this, if you have not yet already done so, please put this in your phone's calendar, set a few notification reminders, be especially mindful that the time is not our normal meeting time. If you show up at 11:10, there's really nothing I can do. You will have lost 40 minutes, which is almost half of the exam period. So please make sure you show up on time, on the correct day. And this will be done the same way as our midterms. This will be in Canvas, proctored by a combination of HonorLock and Zoom. Exam 3, this is our last midterm exam. This is going to be on the last day of class. It's next Friday. In class. Same as all the other midterm exams that we've done. It will be in Canvas, proctored by HonorLock and Zoom during our normal class time. I want to remind you what's covered on this. This covers section 11.8, which is on Intro to Power Series. So this is where we defined what the interval and radius of convergence are. And this is when we answer those questions about the symmetry of the interval of convergence, things like that. It's also where we started talking about geometric series as power series a little bit. We'll also cover section 11.9, which is on representing functions. Oh, I see a question there about test 2 scores. So those have been released for some time. If your exam 2 has not been graded, I need you to go into Canvas and look at the feedback. It means that I'm like missing something from you. There's a reason. So all the exam 2s should have been graded as of like last Monday. So 11.9, representing functions as power series. This is where we integrated and differentiated power series. This is where we used that geometric series trick a whole lot, plugging in different things for the common ratio. And there's 11.10, which is on Taylor or Maclaurin series. And Taylor's theorem, which gave us that formula for the coefficients of a power series for a kind of generic function centered at wherever the fuck you want. This is where we found the power series for e to the x, sine x, cos x, all of that stuff. 11.9 is where we found the series for 1 over 1 minus x, natural log of 1 plus x, and the inverse tangent of x. Other sections that are going to be on the test. 10.1, which is on like sketching parametric curves. So sketching and understanding parametric equations / curves. So this is like, drawing the graph, understanding orientation, terminal point, initial point, all of that stuff. I'll have to take a look. Yeah, so there are a few exams that I haven't marked because I was either missing written work or there was something, the file was corrupted. I'll take a look at yours and send you a Canvas message after class here. 10.2, which is what we've been talking about, which is on calculus with parametric curves. And then the other sections that are going to be on there are 10.3, which is on polar coordinates. And sketching polar curves. And finally, section 10.4, which is on calc with polar coordinates. So these are the sections that will be represented on exam 3. And that test is going to be on the 22nd, which is a week from this Friday. I think announcement-wise, that is everything. Is there anything you guys would like to ask me about the final or exam 3? Okay, I have 2 more quick little things here, and then we'll get into the meat today. First quick little thing. If you haven't seen it yet, I did post a review for the final exam. It's actually 2 reviews. After I finished grad school, I spent a year working for the UF Teaching Center, the College of Liberal Arts and Sciences Teaching Center. It's like their version of the Learning Commons. And while I was working there, I created a couple of reviews for Calc 2. These are based on the final exams that I wrote when I was teaching at UF Calc 2, and it's pretty much the same content that we do here. So I would strongly recommend working through this in preparation for the final. They keep updating it, but the most recent one they've posted was this. So I just grabbed the 2018 one. The stuff below this is not mine. It's not stuff that I made, but it's still really good stuff to practice. Lots of very similar questions, and these are definitely the sort of thing you want to make sure you're comfortable with. And there's a similar thing here, slightly different questions, just more practice if you want it. The other thing I want to talk about is academic integrity. So over the course of this semester in our class, I think I've I've caught 3 people cheating on tests. And I've been as gentle about it as I can. First thing, obviously, please don't cheat. All right, please don't cheat. It's more obvious than you think. And just because I haven't sent a letter to the conduct office, you haven't gotten a call from Dan Rodkin, doesn't mean I haven't noticed. It just means that for whatever reason or combination of reasons, I didn't feel that taking official steps to reprimand the cheating was necessary. There have been some folks who have gotten those calls, and some of those consequences have been pretty serious for them. On exam 3 and on the final, if I see anything even vaguely suspicious, I'm not gonna leave a comment on your work saying to contact me. I'm not gonna do anything except report it to the Office of Student Affairs, and then I'll let them handle it. It's not that I think everybody deserves a freebie for cheating. It's just that I know some people under a lot of stress sometimes make decisions that aren't the best. And we're at a place in the semester now where I really need to know that you know what you're doing in order to be comfortable finishing the term with you as your instructor. So please represent your knowledge honestly on these 2 remaining exams. I know that is stressful, and if there's anything I can do to help you, please don't be shy about asking. If you're nervous about these tests, come to office hours. Come to office hours with questions, and we can work through stuff. We can solve problems, we can talk about concepts, we can talk about test-taking strategies. We can do any and all of the things that might help you perform at your absolute peak on these tests. But I just want to give you a warning that the gloves are off when it comes to academic misconduct. If I see anything remotely suspicious, I'm not going to make any effort to be soft about it from here on out. And I have been soft-ish on it previously in the term because I don't want to see somebody's academic experience tainted or potentially ruined by a bad decision. But we're to a place now where in these last couple assessments, I have kind of no forgiveness left for that sort of thing. So just warning, just letting you know. I think that's it as far as announcement stuff is concerned. So let's go ahead and begin talking about arc length. Arc length is precisely what it sounds like. This is the length of a curve if you were to straighten and measure it. All right, and we're going to talk about this primarily for parametric curves. I will give you a special case of the formula that works for non-parametric curves, like curves where y is f of x, like the ones we saw at the beginning of the semester. But we're going to focus on the parametric case because it is the more general case, and it is the one that sort of makes the most sense geometrically. In terms of the picture, if I have some parametric curve in the xy plane, perhaps with an initial point here, I'm doing, whatever parametric curves do, maybe winding up over here. So this would be my terminal point, and this would be my initial point. So my curve is traversed with an orientation, and you saw that orientation can be an important factor, like when you found the area of the ellipse on the homework set from last week. What we want to imagine doing is taking this, imagine it's made of like a chain or something, and you just pull it until it's straight. So your initial point is here, and your terminal point is here. And then you measure this distance. That would be the arc length. Intuitively very satisfying concept. If you like to think about this parametric curve as a path that some little critter is walking along, maybe there's an ant hanging out in the XY plane and he's just meandering around the plane, walking along this curve. As long as he walks the curve exactly once, right, never doubling back on himself, not repeating it or anything, just walking from the initial point to the terminal point, going along the path, then the arc length would be the distance that the ant walks. As you might imagine, there's a lot of magic here, right? There's a lot of really cool mathematics that goes into this straightening out process. It's not a simple thing. And in practice, we're never going to actually look at the straightened out curve. We're going to have a recipe, a formula that depends on geometry to calculate the arc length straight from this picture. And you don't necessarily need the picture in order to do the calculation. You really just need the formula. But in order to understand the formula, and most importantly, in order to understand what we're going to do with surface area down the road, I want to prove the formula for you. It's not going to be a fully rigorous proof, but let me go ahead and state the theorem. If we have parametric equations, x equals x of t, y equals y of t, where a is less than or equal to t is less than or equal to b, giving a curve traced once as t runs from A to B, then the length of that curve is, I'm going to use L. Most places in the world use a lowercase s for arc length, but for whatever reason your textbook uses L, so to be consistent with their notation, I'll use L, is the integral from A to B, which are t values, remember, so sometimes it's nice to write t equals A to t equals B. I won't do it here, I don't want to clutter it, of the following kind of weird looking thing. It's the square root of dx dt squared plus dy dt squared. So it's that thing under a square root, and the integral is done with respect to t. So this is your recipe. Your formula for arc length. And I'm going to show you where this comes from. We're going to do a little proof, not a fully rigorous proof, just a little one. Remember dx dt, that's what you get when you differentiate the x function. Dy dt is what you get when you differentiate the y function. So the way you would use this is by taking the time derivatives of the two parametric equations, squaring each of them on their own, adding that up, taking the square root, then integrating. traced. The word here is traced, T-R-A-C-E-D, meaning like the ant doesn't turn around and walk back to the initial point and then come back out, meaning we just walk along the curve once in the forward direction. The formal name for these are rectifiable curves, I think. I'm not a differential geometer, but yeah, traced. All right, proof sketch. When you look at the thing we're integrating here, this kind of looks like a Pythagorean thing, right? Like a squared plus b squared equals c squared, but solved for c. And it is. It's precisely that. So let me draw nice and big down here. A parametric curve, maybe with an initial point down here. And the terminal point over here, something like this. The way we do this is we begin by partitioning, meaning chopping up or splitting up. We begin by partitioning the t interval, that's the interval from A to B, into n equal length subintervals. Each of length, call it delta t, which would be b minus a over n. So remember, the horizontal axis here is the x-axis. The vertical axis here is the y-axis. There is no t in this picture. We can think of the t-axis as being like a slider that's down here outside of that picture. This would be t equals a, this would be t equals b. And we think of this as being like a slider. When my slider is over here, I'm at the initial point. As I move the slider to the right, I walk along this curve, right? That's how we've been thinking about these. And we're going to chop this up into equal length subintervals. So A, I will call T0, and then this would be T1, T2, T3. I'll call this Ti minus 1, and I'll call this Ti, just like generic T values in the middle. B we call Tn, so this guy would be Tn minus 1. And each of those T values corresponds to a point on the curve. So the initial point, I'll call this P0. It's the point that you're at on the curve at time T0. Maybe P1 is right here. P2 could be right here. P3 could be right here. The points along the curve are not going to be equally spaced. It's just that the times are equally spaced. The t values are equally spaced. So depending on how quickly we walk through this path. The points, if we're walking very fast at first, then these will be far apart. If we're walking slow later, they'll be close together. And this goes on and on and on. I'm going to label maybe this right here as pi minus 1, and this up here as pi. And the pattern continues on and on like this. The terminal point is Pn. The second to last point here is Pn minus 1. And there would be points, all along the curve. So I'm not drawing all of them. I'll put in a few more here. Like this. Okay. So I chop up my t interval, and each of the little endpoints in the t interval correspond to a point on the curve. Then what we do is we approximate the arc length from one point to the next with straight lines. So I draw a straight line from P0 to P1. I draw a straight line from P1 to P2. I draw a straight line from P2 to P3. And we keep doing that. I draw a straight line from Pi minus 1 to Pi. And we do this all through the curve. Straight line, straight line, straight line, straight line, straight line, straight line. Like this. Maybe I'll put one unlabeled point here, and that way we can kind of complete the picture. All right. Now the blue lengths are not exactly equal to the purple length, right? The purple length is curvy. It's definitely a little bit different than the blue. But if I use more and more points, then the blue length will get closer and closer and closer to the exact purple length. So in the end, what we're going to do is send the number of points, which is n, to infinity. But before we do that, I need to find a formula for the blue length. So that's what we're going to do next. And then once we have that formula, we'll send n to infinity. Everybody with me so far? The reason I gave myself two generic t values is so I would have two generic points. The straight line distance from Pi minus 1 to Pi, I'll denote like this. That's the distance from this point to this point, the blue straight line. I can calculate this by making a little right triangle in here. For which that little segment is the hypotenuse. This vertical distance I'll call delta y sub I. It's how much we go up going from Pi minus 1 to Pi. It's the vertical distance between these 2 points. And the horizontal here, I'll call delta x sub I. It is the horizontal distance between pi minus 1 and pi. Then I do have a little right triangle here, which means that this distance squared is equal to delta xi squared plus delta yi squared. Because for any right triangle, a squared plus b squared equals c squared. And this means that that distance, the straight line distance from pi minus 1 to pi, is the square root of delta xi squared plus delta yi squared. Okay, everybody with me so far? Take the purple curve, drop a bunch of points on it, corresponding to the chopped up time interval. This is the distance from any one point to the next point along that straight line path, not along the curve, but along the straight line path. The reason it's nice to have the generic pi minus 1 to pi is because if you plug in I equals 1 here, you get the distance from p0 to p1. If you plug in I equals 2, you get the distance from p1 to p2. If you plug in I equals 3, you get the distance from p2 to p3, and so on. Which means that the total distance of the straight lines which is approximately L, the total distance of the straight lines is the sum from I equals 1 to n of the distance from pi minus 1 to pi. So when I is 1, that gives you this distance. When I is 2, that gives you this distance. When I is 3, that gives you this distance. When I is 4, it gives you this distance. If you add all of those up, you get the length of the blue straight lines. And plugging in what we just discovered a second ago, this is the sum from I equals 1 to n of the square root of delta xi squared plus delta yi squared by Pythagoras. And this is approximately L. Well, L, remember, is the exact arc length. Of the purple curve. So I'll write L is approximately equal to this. And like I said, that approximation gets better and better the bigger and bigger n is. So at the end here, we're going to send n to infinity, and this is going to turn into a Riemann sum for this integral, right? You can kind of see the similarities between the sum down here and the integral up here. We just need to do some algebra here to turn this into a Riemann sum for this guy. Let's get into the algebra. I want to do the integral with respect to t. which means I need to introduce a delta t term. And the way we do that is by multiplying top and bottom by delta t. And then the delta t, which is downstairs, I'm going to write as the square root of delta t squared. The delta t, which is upstairs, I just peel him off of that fraction and let him chill. Now I have this square root times 1 over this square root. That will allow me to stick that delta t squared inside my big square root, giving me this expression. And then finally, I will distribute this 1 over delta t squared to these two terms under the radical. So I get the sum from I equals 1 to n of delta xi over delta t all squared plus delta yi over delta t all squared times delta t on the outside of the root. So the delta t downstairs here, it's a positive quantity. So I can write this as the square root of delta t squared. So this piece is this piece. All right, if you simplify this fraction, this is 1 over delta t. And then multiply by this, you get delta t over delta t. So I'm just rewriting the piece downstairs as the square root of itself squared. It's a sneaky trick, and I'm doing it because I want to shove a delta t into this square root so I can get derivatives out of these things. Right, because we know what we're shooting for. We know what the integral looks like. I want dx dt and dy dt in my integral. So I need this and this to be divided by delta t. Not really, but be mindful, this isn't an exercise, this is a proof. So in your homework problems and your test problems, you won't be doing this, you'll just be using the formula. I'm just trying to show you where the formula comes from. Okay, so now as n goes to infinity, a few things happen. First, L becomes exactly equal to the result, right, which is the limit of this Riemann sum. 2, delta t becomes the differential dt, and 3, these guys, delta xi over delta t, that becomes dx dt, and delta yi over delta t becomes dy dt. Therefore, L is equal to, I should say, so this is a Riemann sum for L equals the limit as n goes to infinity, sigma I from 1 to n, square root delta xi over delta t all squared plus delta y over delta t all squared times delta t, which is, by the definition of the definite integral, the integral from a to b of the square root of dx dt squared plus dy dt squared dt, which was the formula we were trying to prove. So victory. And that's it. I'll hold here for just a second. Any questions or anything we'd like to look at more closely there? Okay. Let's start with a nice, easy example. Let's find the arc length of the parametric curve x of t equals r cos t, y of t equals r sine t, where t runs from 0 to 2 pi. To do this, I will use my formula, which involves dx dt. So if x of t is r cos t, then dx dt is the regular time derivative of that, which is negative r sine t. I know my formula also has dy dt in it, so I need to calculate that. The derivative of r sine t, r here is a constant, is just r cos t. Therefore, the length of this curve should be the integral from 0 to 2 pi, right, from a to b, the bounds for my t values, of the square root of dx dt squared plus dy dt squared dt, which is the integral from 0 to 2 pi of the square root of negative r sine t squared plus r cosine t squared dt. Generally in these problems, the big task is to simplify the stuff inside the square root. Because you have a square root with a bunch of stuff squared underneath, you are often going to run into trig sub. Now, this integral is very, very nice, but many of these integrals are quite terrifying. This time, though, if you take negative r sine t and you square all of that, you get positive r squared sine squared t. If you take r cosine of t and square it, then you get r squared cos squared t. So my integral becomes this. And you have a common factor of r squared. So this is the integral from 0 to 2 pi of the square root of, if I factor in r squared inside the square root, what's left here is just sine squared t plus cos squared t. And you know that sine squared t plus cos squared t is 1. By the world's most useful trig identity. So this is just the integral from 0 to 2 pi of the square root of r squared dt. And r squared is a constant. R is a constant. The square root of r squared is just r. So what do we get? We get r times t evaluated from 0 to 2 pi. And that's r times 2 pi minus 0, which is just 2 pi r. And this should not come as a surprise. Why should this not come as a surprise? What is the parametric curve I'm working with here? Yeah, it's a circle, right? This is a circle of radius r centered at the origin. So the arc length of that circle would be its circumference. Modulo my bad r. Right? This is a circle of radius r that we traverse exactly once. So this is the circumference. Radius. It's r, which we know is 2 pi r. Not bad, right? Now I can modify this problem just a little bit and make it considerably more challenging. And I am going to look at this modified version. Before I do that, any questions on any of the steps here, where any of the pieces came from, or why this is not a surprising result for us? Yep. Yeah, as long as you're comfortable with this formula, they are straightforward computations. The challenge is that sometimes the computation itself can get quite hairy, right? So we know integrals can be hard, especially integrals with square roots. Before I dive into this next problem, I want to actually talk about the graph for a second, because it's a cool curve. Let's talk about this guy. So if you compare this to the previous problem, instead of an R for the radius here, we have a T. Everything else is the same, right? Well, I guess I've switched the signs and the cosines also, but if this was a constant, like a 2 sine t and 2 cos t, that would still be a circle. It would be a circle of radius 2. But here the radius is variable. So as t goes up, normally that walks us around the circle. Here, as t goes up, that walks us around the circle, and the radius is increasing. So what kind of shape are we going to get out of this? So here the curve is like a circle, but the radius increases as we go around. There's a common English word for curves like that, shapes like that. This is a spiral. Particularly, it's an Archimedean spiral. And I can show you in Desmos really quickly. So from 0 to 1, it's not that interesting, but if I open this up, you see, yeah, it's a spiral. Pretty cool, right? I'm going to stick to the 0 to 1 part because I want my bounds of integration to be nice. Let's jump in and see what we can do with this. Dx dt is now the derivative of t sine t. That requires the product rule. So that's going to be 1 times sine t plus t times the derivative of sine t, which is cos t. And dy dt, also a product rule. If I differentiate this, I'll get 1 times cos t and then plus t times the derivative of cos t, which is negative sine t. So that's minus t times sine t. Which means that L, my arc length, is the integral from 0 to 1 of the square root. This is going to be quite large, so dx dt squared, that's sine t plus t cos t squared plus dy dt squared, which is cos t minus t sine t squared. And all of this is under the radical and dt at the buoy. Quick reminder, the square root and these squares do not cancel because of this addition, right? If you've got things added up under a square root, you can't take the square root separately. Square roots do not play nice with addition or subtraction. So can't get rid of the square root easily. What I'm going to have to do here is FOIL everything out and hope that a bunch of stuff goes away. Now we have a sine t in here, and this whole thing's being squared, so there's going to be a sine squared t. I have a cos t in here, and this whole thing's being squared, so we're going to have a cos squared t. You know those add up to 1. Sure, yeah, the note just says the curve here is like a circle, but the radius increases as we go around. dot, 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 a spiral. So I'm going to go ahead and FOIL things out here. Instead of drawing the big square root, I'm going to put like bracket and then put everything to the 1/2 power, because it's going to be like a ridiculous looking square root otherwise. Foiling the first piece gives me sine squared t plus sine t times t cos t times 2, right? 2 copies of that, so plus 2t sine t cos t plus t cos t squared, which is t squared cos squared t. So that's the first piece. And then I'll have plus the second piece foiled out is cos squared t plus 2 times this. So it's going to be minus 2t sine t cos t. Oh, it's going to be close. Can we fit it? Yeah, I think so. And then the last term here is going to be t squared sine squared t. All to the 1/2 power, and the dt. There it is. Okay, we got it. See what I mean, right? So yeah, knowing the formula will get you going. But many of these problems, long. There is a lot of good news here, though. I have a plus 2t sine t cos t here. I have a minus 2t sine t cos t here. Those kill each other. I have a sine squared t here and a cos squared t here. We talked about those. And then I also have these guys, t squared cos t and t squared sine t. So I will put these guys together as the underlining suggests. And that will give me the integral from 0 to 1 of bracket sine squared t plus cos squared t plus, now from these guys, I'm going to factor out a t squared. And I'll have from that sine squared t plus cos squared t as well. All still under a radical, or if you prefer like I am, writing it to the 1/2 power. And just like the square roots don't distribute, the 1/2 power doesn't distribute. We can't do that. Gotta handle it like this. But there's more good news here. Sine squared plus cos squared. Sine squared plus cos squared. Each instance of that is 1. So this is really 1 plus t squared times 1, all to the 1/2 power. In other words, this is the integral from 0 to 1 of the square root of 1 plus t squared dt. And now I am required to ask if anybody remembers how to do this integral. You may have some trauma associated with this integral. Yes, sir. So the correct answer came in the form of a DM. It is trig sub. Can anybody tell me what the substitution is? And subbing for t squared would be a u sub. If I had a t on the outside, I could do that. But without a t on the outside to soak up the differential, yes, tangent. Tangent is correct. So this requires the trigonometric substitution. T equals tangent theta. We need our differential, dt, which will be secant squared theta d theta. And the other thing which we must do, it's not optional, remember, I will take off points if you don't, is change your bounds. When t is equal to 0, we get 0 equals tangent theta. Taking the inverse tangent of both sides, we get inverse tangent of 0 equals theta. The inverse tangent of 0 is 0. So when t is 0, theta is 0. When t is equal to 1, plugging 1 in here, you get 1 equals tangent theta. So theta would be the inverse tangent of 1, which is pi over 4. So that is your trig sub. When I plug this substitution in, I get the integral from 0 to pi over 4 square root of 1 plus tangent squared theta times the differential dt, which is secant squared theta d theta. You will encounter trig sub in this section, and it is very important that you handle it correctly. It's been a while since we've done trig sub, I know that. The things people really mess up and forget, they forget to plug in for dt. Don't forget this. Always write your differentials. That's a good way to remind yourself that you need to plug in for dt when you do the substitution. The other thing people forget, of course, is changing the bounds. So if either of those things feel rusty, uncomfortable, whatever, go back and study section 7.3. Come to my office hours. We can talk about stuff. Go look at the modules. There's lots of good stuff in there. One plus tangent squared is secant squared. So I have the square root of secant squared theta times secant squared theta d theta now. And your spidey senses might be tingling. You may be experiencing some PTSD because this is secant cubed. I have here the integral from 0 to pi over 4 of secant times secant squared, which is secant cubed theta d theta. Who remembers how to do this integral? Very good, looping IBP. All right, I told you there was a reason we did all that shit at the beginning of the term. The setup here is, remember you pick U and dV. dV is going to be secant squared theta d theta, and U is going to be secant theta. Du and V would be what you calculate from them. I'm not going to show all the details of the looping IBP because we do not have time. At the end of the looping IBP, you get 1/2 secant theta tangent theta plus the natural log of the absolute value of secant theta plus tangent theta. And this will be evaluated between our bounds, which are 0 and pi over 4. So let's just track this problem for a fucking second here, because this shit's kind of crazy. You start with your formula for arc length, dx dt, dy dt, you square them, you add them, you take the square root. Blow everything apart inside the square root, collect like terms together, cancel what cancels, group what groups, and then use some trig identities. That leads you to this integral, which requires trig sub, which leads you to this integral, which requires looping IBP. These arc length problems are no joke. In order to evaluate this and this at pi over 4 and 0, obviously we need to know the secant of pi over 4. We need to know the tangent of pi over 4. We need to know the secant of 0. And we need to know the tangent of 0. So one at a time. What is the secant of pi over 4? Square root of 2. Yeah, it's the square root of 2. Right, it's 1 over the cosine of pi over 4. The cosine of pi over 4 is root 2 over 2. So it's 2 over root 2, which is just the square root of 2. The tangent of pi over 4 is 1. The secant of 0 is 1. And the tangent of 0 is 0. These come from the unit circle, and we need to know them. So when I plug in my shit here, I get 1/2 times secant of pi over 4 times the tangent of pi over 4. That's the square root of 2 times 1, which is just the square root of 2. plus the natural log of the absolute value of secant of pi over 4 plus tangent of pi over 4. Well, that's root 2 plus 1. So there's my upper bound plugged in. Now, what about when I plug in my lower bound? Well, when I plug in 0, I get 1 times 0 here, which is 0, plus the natural log of 1 plus 0, which is the natural log of 1. And the natural log of 1 is itself 0. So I only get anything from this first piece here. And since root 2 plus 1 is positive, the absolute values can go away. So I get 1/2 times the square root of 2 plus the natural log of root 2 plus 1. And that is the end of the game. So you see, even with me omitting stuff, right? Like I didn't do the looping IBP here. This is not a short problem. This is a rather long problem. And they actually can get much, much worse. In fact, many arc length integrals are straight up impossible. Cannot be done. Unless you're willing to use power series, which is why we do power series before we do this section. Now, I'm not going to do that to you, just to be clear. I could in theory, right? And in theory, you should be prepared. But the reason we do power series before we do arc length is because many, many curves, when you try to calculate their arc length, give you something that you cannot integrate by hand, right? There is no closed form antiderivative like some of the functions we looked at in section 11.10. So having the ability to expand your thing as a power series is a very useful tool to have kind of in the real world when you're attacking arc length problems. This is not bad. One particular problem that I want to discuss with you just for a minute is the arc length of an ellipse. I'm not going to set it up right now, but I'll actually, we have time. Yeah, we can do surface area. No, that's mean. But the arc length of an ellipse, if you try to just plug in for any of the ellipses that we were working with last week, graphing parametric curves, if you try to plug into our arc length formula to find the circumference of an ellipse, you'll get an integral that nobody can solve. And it actually started a whole new branch of mathematics called the study of elliptic functions. So the circumference or perimeter of an ellipse, you can approximate it, but you cannot find it exactly. There's some cute stuff here, right? Unfortunately, there's no simple way to express parameters in terms of elementary functions. Elliptic integrals are integrals that are similar to the integrals you get when you try to find the arc length of an ellipse. These are best expressed in terms of what are called hypergeometric functions or the standard elliptic functions, which in the universe of mathematics I participate in are doubly periodic complex valued functions on the complex plane. They are quite beautiful. They are very, very special functions, but way beyond the scope of this class. So the last thing I'd like to do, since we don't really have time to dig into surface area much today, I think it could not hurt to do more. Well, no, maybe let's introduce the surface area stuff. We've seen some examples of the arc length problems. Let's get you ready to talk about surface area, because that's what we're going to be doing next time. So surface area is a two-dimensional measure. If you take a ball, like a basketball or something, that has a surface area. If you were to cut up the ball and like flatten it out, then the area of that flat shape would be the surface area of the ball. A piece of paper has a surface area, right? It is a surface. And no matter how I deform the paper, what I do to it, the area of the paper stays the same. We're going to look at surface areas for solids of rotation. So remember, I mentioned last week that we would be kind of shifting back to that mentality we had in chapter 6 when we were finding volumes. Back then, what we did to find the volume for a solid of rotation is we look at the region that you're rotating and we drew a little strip in there. We rotated just that strip and that gave us like a little disc or maybe a little washer. We found the volume of that little disc and then we integrated that to get the whole volume. What we're going to do here, we're going to take our parametric curve. And I'll draw this so that it's fairly simple, like maybe something like this. And we're going to revolve it either around the X or the Y axis. I'm going to draw this like we're going around the X axis. I'm not rotating the whole region, right? I don't care about like the space under the curve. I'm just going to rotate the curve itself, which is going to produce a surface. And that surface, in this case, would look something like this. I know modulo my bad art. Something like this. Like a flower vase. And I want to find the surface area. The way we do this, kind of analogous to the volume problem, is by taking a little piece of arc length. Along the curve. And we call this ds. The standard notation for arc length is S, by the way. Your book uses L. I don't fucking know why. It's really annoying. Everybody in the universe uses S for arc length. I think they wanted to avoid confusing like surface area and arc length, but then they use ds and it's just bad. It's bad. It's all bad. But we're going to take just a little smidge of arc length here. And I'm going to see what happens if I rotate just that little smidge of arc length. So here is that little smidge of arc length in our solid on our surface. And if I were to rotate just that guy, it would produce a little band of surface area. And what I want to do is measure the area of that little band. Produces think like a watch band, right? And I'll call this EA, A for area. So now the question is, how do you find the surface area of a little band like this? Well, if you wanted to measure the surface area of your watch band, you would take the watch off and lay it down flat on the table and then measure it. So it's that same sort of cut and unroll procedure that we used for the cylindrical shells method when we talked about volumes. I'm going to cut and unroll this tiny band of surface area. I know that this length here was ds, which means that this dimension here is ds. And that is this dimension of my unrolled band. What is the other dimension? What is like the width here, the length of my unrolled band? Very good, it's the circumference. Which is 2 pi times the radius of the band. And in this case, that radius is y. So the surface area of the band, I should say the little surface area of the band, is dA equals 2 pi y ds, where ds is the little piece of arc length. And the little piece of arc length is the thing you integrate to get arc length, which is the square root of dx dt squared plus dy dt squared times dt. So dA would be 2 pi y times the square root of dx dt squared plus dy dt squared times dt, which means your full surface area we'll call A would be the integral from A to B. These are t values. The t value at the left is A. P value at the right is B of dA, which is this thing. And from t equals a to t equals b, which is the integral from a to b of 2 pi y times the square root of dx dt squared plus dy dt squared times dt. It's a little bit much, but with practice, this will feel more and more natural. And the key to understanding the key to understanding surface area is to understand arc length. Next time on Wednesday, we're going to talk more about this thing, ds, the little piece of arc length. And we're going to do a few things with it. We're not just going to cook up surface area. I will also show you how to find the surface area when you rotate about the y-axis. That's a slightly different thing. Your circumference is no longer 2 pi y, it'll be 2 pi x. And we'll practice doing a handful of computations with this formula and the related one that comes from rotating about the y-axis, where this becomes an x. But for now, that is enough for today. The homework set that I'm going to be opening for you in the next few minutes has lots of arc length problems and a few surface area problems. Some of the arc length problems ask you to calculate the arc length exactly. Some of them ask you to just come up with a formula for the integral that represents the length of the curve. That's because it's not an integral that you can solve easily. And in those cases, it will tell you to go ahead and approximate that using a calculator. You can use whatever tool you want for those. I don't care, Symbolab, Wolfram, whatever. But the important thing is that you get comfortable setting up these integrals, and that the integrals which you can solve, you remember how to solve, because you'll have to do that on the test. So tricks like trig sub and all of that good stuff, u sub, everything that we did at the beginning of the semester is back again. But the good news for you is that, no more infinite series, right? No power series here, no infinite series, no convergence tests, none of that. Next time, we're going to talk more about surface area. We're going to talk more about applications of this little piece of arc length thing we call ds. And then we will be moving away from parametric equations and starting to talk about polar coordinates. But that will be for next week. So I'm going to go ahead and end the meeting here. Are there any burning questions you guys would like to ask before we wrap up? Okay, then that's it from me. Ro, I'll take a look at your test and see what's going on there. Otherwise, I will see you guys and talk to you next on Wednesday. Take care.